This video is for lesson 5.3, function rules, tables, and graphs. So in this lesson, you are going to be reading about independent and dependent variables, which you should already be familiar with from science, but just a refresher, the independent variable represents the x values, or the domain, and the dependent variable represents the y values, or the range. So whenever graphing, the independent variable is always on the x-axis and the dependent variable is always on the y-axis. For these three examples, identify which would be the independent and which would be the dependent variable. For the first example, it costs $1.29 to download one song from iTunes and $3.87 to download 3 songs. The independent would be the number of songs, and the dependent would be your total cost, because your cost depends on how many songs you purchase. For the second example, the larger the school choir, the more buses must be rented for their trip to Harrisburg. The independent is the number of people in the choir, and the dependent is the number of buses, because that depends on how many people there are in the choir. Now this third one can be interpreted a few different ways. It says the longer you drive, the less gas will be left in your car. Some people will say that the independent is the number of hours, time, and the dependent is the amount of gas left, which is typically correct because the amount of gas left depends on how many hours you drive. But I've also heard the argument, well, couldn't it be the other way around, because you can only go so far, so the number of hours you can drive depends on how much gas you have in your car. Technically, that could also be true for this one. So you could really graph either one on the two axes, depending on whether you're like subtracting from the total amount that you have, or if you're like looking at it the other way around. But I think for this one, it could go either way. So there are many different ways to represent a function. We've seen almost all of them at this point, I think. A function rule is an equation. We've seen those. A table, we've seen those. And then a graph is another way to represent each function. So in this lesson, we're going to be talking about how to show function rules from an equation to a table to a graph. Now, we've done this a little bit using the Desmos and the graphing calculator. These ones we're going to be doing by hand, where we actually are interpreting and calculating the values. So when we're graphing a function, I want to make sure that you are choosing at least 5 values for your table, 2 that are positive numbers, 2 negative numbers, and 0. This can help us get a nice, good overall picture of our graphs if we just pick a couple points, 1 or 2. Well, 1's not enough because then we don't know what it looks like. 2 is only going to connect every time to look like a straight line, so that's not good enough. 3 is okay, but it doesn't give us a nice, clear picture. So 5 is a good number. If we get 2 negatives, that'll give us stuff on the left side of the graph. 2 positives should give us some information on the right side of the graph. 0 right nice in the middle, and that'll give us a good picture. So for this first example, like I said before, you're going to pick 2 negatives, 2 positives, and 0. I tend to pick the opposite, like positives and negatives, just because generally speaking, once you calculate the negative, then it's easier to calculate the opposite, the positive. So I'm going to pick for this one even numbers because it's a half. So -4, -2, 0, 2, and 4. You really could pick anything. I want these to fit on my nice graph though, so I don't want it to be too crazy. This middle column is for us to evaluate the function if you need to some space to show your work. You can also do it in your head, most likely, for some of these, but it's nice to have somewhere to write it down. So this middle column, I'm just filling in. I'm replacing the x with each of my x values that I chose, and then I just need to evaluate them. So half of -4 is -2, plus 3 is 1. Half of negative 2 is negative 1 plus 3 is 2. Half of 0 is 0 plus 3 is 0. Half of 2 is 1 plus 3 is 4. Half of 4 is 2 plus 3 is 5. So then after I make my table, I can make my graph. Negative 4, positive 1. Negative 2, positive 2. 0, 3. 2, 4. And 4, 5. And there's my graph, which is a nice straight line. Connect the dots, arrows on the end because it goes on forever. So you might remember from our little investigation with calculators and the Desmos that this would be a linear function because of the way the equation looks. It just has an x, doesn't have absolute value, it doesn't have the quadratic, the square, x squared. So that's how we knew this would be a straight line. This is an absolute value. So you remember from our calculator and Desmos examples, it's going to look like a V. So you can really pick any. I'm going to just pick the same ones that I did in the last example, just for consistency. And then you're going to evaluate the absolute value of each plus 1. So, whoops, that should be a positive 4. So for these, you'll notice you actually get the same y values for the negatives and the positives, and that's okay because remember we want it to make a V shape, so that makes sense that it will repeat itself on the right side and the left side, just with the positives and negatives. So we have down, up, arrows on both ends because it does keep going, and that is our absolute value graph for that equation, the absolute value of x plus 1. And for our last example, we have a quadratic. I'm actually going to pick some smaller values for this one just because when you square them, they get kind of big. Don't forget, you have to put the negatives in parentheses. If you don't, you will get the wrong answer if you're typing them into your calculator. Negative 2 squared is 4. If you don't put the parentheses and you type it into the calculator, you're going to get a negative 4, and that's wrong. So 4 minus 2 is 2. This is 1 minus 2 is negative 1. 0 minus 2. 1 minus 2. And 4 minus 2. So again, just like absolute value, the quadratics repeat themselves. And if you remember from our absolute value, or from our graphing calculator examples, these look like a U. It's kind of hard to tell the U versus the V a lot of the times, but this is what this one will look like. Especially even with five values, that can be hard to get a good picture for the U versus the V. All right, and for our last example, we're going to compare these two different scenarios by plugging in some different values. I'm going to use the same values for all of them, and for these ones, I'm going to use only positives. Now that breaks my own rule, which I'm aware of, but I'm going to use only positives because in these scenarios, X is representing the number of CDs, which I don't even know if you guys know what a CD is at this point, but CDs can't be, number of items can't be negative, so we're going to use positives only. So if you take some time to fill in based on each individual scenario's equation, so we have on the left, we have 50 plus 3x, and on the right, we have 25 plus 8x. So if I evaluate each of these, I'm going too fast and making mistakes. I'm going to get two different sets of results because I have two different equations. So this is $50, $53, $56, $59, $62, 25, 33, 41, 49, and 57. The question that we want to talk about with these scenarios is, Is there a point where it is less expensive to buy from Snoop Unlimited? So if you notice, the Snoop Unlimited starts out, it is more expensive, but by the end of just 4 CDs, you can see they're getting closer in value. So I didn't do 5, but if I did 5 for each of them, this would be $65. This would be $64. So you can see they're getting closer and closer and closer. The point where it's cheaper to buy from Snoop Unlimited would be 6 CDs. So anything below 6 would be cheaper, more expensive at Snoop and less expensive at Drake and Company. And above 6, it's going to reverse. It's going to be more expensive at Drake because there's more cost per CD and less expensive at Snoop Unlimited because it's cheaper per CD. There's just a larger upfront cost. So that's the point where they would flip. And then I already explained this a little bit. The unreasonable domain and range values would be negatives because you can't purchase a negative number of CDs, and you also can't, you can spend a negative amount of money if you borrow money, but in this scenario, since you can't purchase negative CDs, you wouldn't have negative amounts of money.